How you doing?
Good. I was just wondering if I should...
No. No. No.
Welcome to the Banff Mountain Film Festival Radical Reels Tour, a program of the Banff Centre with presenting partners National Geographic and the North Face. National Geographic. Celebrating 125 years of exploration, and the adventure continues.
So this used to be something, I didn't see it this year. This is something that was on at the State Theatre this time last year. It's a kind of traveling show that comes around each year, I thought, but I couldn't find it this year, so it's not quite so relevant as it was in the past, but an interesting thing to go and see nonetheless. You can decide yourself whether it relates to some of these things, how they relate to fluid mechanics, but many of them do, as you know, can work out. Sorry? All through class? Yeah, sure, let's do it.
Inspiring the next generation to never stop exploring.
So what else? What of these things do we want to do? I want to do beer bottle tapping.
Ready? Go. Go. Start chugging up. Don't you let that shit pop out. Go.
Come on, Dustin.
Oh, my record's already up.
Yeah, pretty poor performance, right? Not very fast.
Come on, you're gonna get beat by girls.
Of course, there's some fluid mechanics relevance to this. I mean, what's happening here? You know, we're talking. What's the mechanism by which that works?
Come on.
Would it work in soda? That probably is soda, right? Of course. Pop. Not sure what you call it. Soda, I guess, right in this country. So, what's any idea? There's a good presentation problem for you right there. What's the mechanism by which it works? We're talking about waves. My best guess is it's a wave that goes down the bottle. When you tap the top of the bottle, it hits the base of the bottle, gets reflected as a extensional wave, tensile wave. It cavitates the water by pulling the gas out of solution and nucleating it, and it froths. So I would guess that that's the mechanism for that. So anyway, so something like that, simple question like that, is a good one for your presentations. Anyway. And so, finally, so today...
The sport in our story tonight is called free diving, and it involves going down hundreds of feet on one single breath.
So, today, I trust you had a good break, safe break. I guess safe if you're here with us today. Today, we're going to take it the next step. We're talking about fluid properties. On a couple of occasions, we met last week to talk about fluid mechanics rather than introduction. And so what we'd like to be able to do is to be able to take our knowledge of what we now know about fluid properties. We talked about some key fluid properties which govern behaviors that we're interested in. Those would be things like viscosity, density. We didn't get to talking about vapor pressures and surface tension, but you can look at the linkages in the videos to see that. It's linked on the kind of resources page, so please do look at that. And so what we'd like to do is now is be able to use these in some useful way to be able to say something about some physical systems that are of interest to us. And some of those systems might be such as this kind of, not so frivolous, I guess, but not really related to, in a professional way, to the kinds of things that you might want to do. But we'd like to be able to look at pressures. And fluid pressures not just at a point, but how they might vary from that point in first a static fluid and then in moving fluids. And so it's important for us to be able to do that for a variety of things. If you go swimming, of course. This is talking about free diving, where people fill their lungs up with air and then go down a couple of 100 meters in the ocean, down to, it's links in pearl diving, I guess, and then try and see how far they can go down and come back up. And so clearly there's a change in behavior as you go down from the surface where the pressure is atmospheric to much deeper down where it's some different pressure. It relates to other things that are going on in the news. Maybe the eruption in the Icelandic volcano is driven by fluid mechanics. It's driven by magma rising by buoyancy, hitting the surface, gas charged, breaking into ash as it hits the surface and solidifies, and then being lofted up into the air where it's a hazard to aviation, and can do a steam clean job on jet turbines with not very good results if you happen to fly into that, as we saw from the KLM situation maybe one of our previous times. And it relates to the Macondo incident, was it 3 years ago now, in the Gulf of Mexico, where excess pressures in a well blew the well to the seabed, and with the consequences to the outflowing of hydrocarbons from an unstaunched reservoir, which had a relatively large environmental effect. And I just heard on the news this morning that Halliburton finally settled for $1 billion for their part in this, of deleting data related to the incident and other misdeeds, I guess. And so all of these things relate to our understanding, if you like, of fluid pressures and how they change. And so what we'd like to do today is maybe talk a little bit about some of those behaviors so we can actually be able to calculate what those fluid pressures might be as they might affect structures that we could be interested in. So that's our plan for today. So our outline it follows exactly from where we are dealing with, on course for this point, beginning of second week. And what we'd like to be able to do is say something about how fluid pressures vary as we go from a point. So what we'll do is we'll figure out exactly where this comes from and what it means, and then we'll try applying it in a very simple case to incompressible fluids such as water, and to compressible fluids, which would be gases, which behave in slightly different ways. And so that's a broad interest that we have in being able to do this. And so I'm going to take this excursion to be able to do things with this. So I'm going to write some things down so you can keep up or choose to not keep up with me as we go through this. And so what I want to do today is talk maybe about fluid statics. So it's second week, first class. See how my handwriting is? Not bad, even if I say so myself. And so what do we know about the systems that we're dealing with? Well, we know, for instance, that if we, maybe in the radical real stuff, we know that if we go from sea level to the highest point on Earth, which is Everest, which is about 30,000 feet, 29 something, right, and change, which is about 10,000 meters, which is about the same height that planes fly. Certainly in a plane, we're protected from the exterior environment, both the cold, because it's minus 60 centigrade out there, and also the very low pressures. We presume that low pressures. But you know that when people climb mountains, they take oxygen. They take oxygen because the air is thinner, quote unquote. Thinner means it's less dense. And the reason that there's less pressure is because there's less material directly above you as you start climbing. And so the easiest way for us to think about calculating exactly to get a rough ballpark magnitude of how pressure might change as you go in elevation is to take a container maybe and to look at the weight of that container, which we know is going to be equal to the height of this, whatever that height might be, call it Z to be consistent. And the weight is going to be the unit weight times the height, which is the same as rho g times the height. So that gives us the absolute weight that's applied on this. If we know that the cross-sectional area of this container, this fictitious container that we have, that has no weight except for the material inside it, which is air, we could calculate, for instance, the pressure that we'd have to apply on this base to be able to hold this up, which is going to be equal to the weight divided by the area. Okay, so this is the weight. Actually, I misspoke, right? So this is also has to be pre-multiplied by the area, because this here, by definition, is our volume of our system, in the very simplest case. And so if we take this weight and we divide it through by rho g z a, and we divide by a, which is really what we're doing here, then we know that the pressure is equal to just the unit weight of the fluid, rho g, is equal to rho g times z. And so we can take some numbers for this. The density of air is about of the order of 1 kilogram a cubic meter. We know that gravity is roughly 10 meters per second squared. 9.81, of course, but 10 is close enough. And so if we multiply those together, then the unit weight of air is something like, of the order, approximate 10 newtons per meter cubed. So it's a force per unit volume. If we multiply it by elevation, by 10,000 meters, then this becomes 10,000 multiplied by 10 newtons per, this becomes, 10,000 becomes 10 to the 4, so times z, so this is 10 to the 4. So this becomes roughly of the order of 10 to the 5 newtons per meter squared. Which is curious, right? It's curious because atmospheric pressure is exactly that in SI units. It's 100 kPa, or 10 to the 5 pascals. And so clearly there's something in this which might be a little off, and that suggests that if this is atmospheric pressure here at 100 kPa, this is due to the weight of this material that's sitting on top of us. So if we go up to the top of this and do the same calculation, then we'd find out that the pressure up at this elevation was 0 kPa. And certainly the pressure on top of Everest isn't 0. It's relatively low, but it's less than that. It's higher than that, rather. And so there's something wrong with this calculation. And so what's wrong with this calculation? So we haven't really talked about our assumptions, but we've assumed that the density of air is constant, and it's the same as the magnitude that we're seeing here. As we go physically up into higher elevations, because there's less pressure, there'll be less molecules of air in a given volume, and so the density will decrease. And so we've made an assumption, which is not a bad assumption. It actually gives quite a good result, but it's one that's not going to be good enough for the kinds of things that we do here, and so we need to be able to do something better. And so the basic outcome from this, of course, is that if you want to calculate pressure, we have this relationship here. The pressure is equal to density times gravity times elevation, which we can also write, well, as equal to unit weight times elevation. And this actually is very similar to something that we've already looked at today. So, for instance, we could take this and we could differentiate both sides. And we'd end up with an expression which is change in pressure with elevation equals unit weight. And it's as straightforward as that. And so we've seen that this morning. I'll come back to that, don't worry. We've seen it here. It happens to be a negative sign there. It happens to be a partial derivative, but we don't need to worry too much about that. But basically, this is an expression that we can use to be able to say something about how pressures change as we go up and down in a column of fluid. And although we've done it without very many assumptions and haven't said anything, this is actually an expression. The true expression, of course, would be the one that we've talked about. dP dz is equal to minus unit weight. And the minus sign is just because of the sign convention that we'll ultimately choose for our coordinate system, our right-handed coordinate system. And so that's a fundamental expression that we are interested in being able to use. The extension of that, of this, very simple analog, of course, as well, it's quite useful, is that we could also do this to be able to look at, for instance, how pressure changes as a function of elevation. And here we'll draw our elevation going down vertically downwards. But remember that our sign convention ultimately is going to be with the z direction positively upwards. And we could do this small construct to take a bucket of air, or any other fluid for that matter, and to place it at some point where we want to be able to measure the weight of that. And if we did that, then we'd come up with some pressure due to this, which is the same calculation that we've done here. We calculate the pressure as a function of the height of this individual container. And so if we plotted this magnitude of pressure that we calculate at relative to depth, then we'd end up with a single magnitude. If we take a second container of this and then stack two of them on top of each other, where the elevation now is 2z, my z's always have a line through them, my 7's always have a line through them, then this would be equal to twice that pressure as well. And so if we drew the individual components here, then we'd end up with a straight line that goes down through these, which I'm not drawing very well, but you get the picture. And so if the density of this fluid in this container is constant, then this line is also a straight line and doesn't change with depth. If density is not constant, then it's going to deviate from that. And you can probably do the thought exercise to think about how it might deviate from that. And I suppose, how would it deviate? So if you started off at this point here, and this is your sea level location, and you went up from there, and it's air which is maybe gets less dense with height, would it look like this? Or would it look like this? It has to go through this point, right? So as it goes up in height, you could imagine that if the density is not constant, then this would be heavier than this. And so I suppose if you're going from this magnitude and you go across some magnitude from here, you'd expect that you'd go up on a trajectory like this. So the other thing that we'll find out, so this is density changes with pressure. And so we've made the point that this partial derivative dP dz equals minus unit weight is absolute, and it is absolute. But it's only correct if we look at it incrementally along this line of this trajectory. I'll redraw this. And so really what that term is saying is it's basically saying that, so let's see, if this is our system here, this is pressure, this is elevation, then really what it's saying is that at any point, take any point here, we can draw the tangent to this pressure versus height curve, and there'll be some change in pressure as we go, some elevation change. And so this relation really is true, and that is that change in pressure with elevation is equal to unit weight. It's positive in this case just because there are sign convention. So we'll work out the issue about the positive and negative component of this, the precursor bit in front of this equation. So that's really all it's saying. So this, plus or minus, let's not worry about it now. This is always absolutely true. This is only true if the fluid is incompressible. So it's not very good approximation if we're looking to calculate pressures as we go up in the atmosphere, or pressures as they vary maybe in gas fields, for instance. And so that's the first lesson maybe that we have to have. So this is so just remember that. This is always true. This is not always true, and we have to do something to deal with that. So that's one way of being able to look at these behaviors. So when we look at fluid statics, we'll also look at the behavior for accelerating fluids. And so that seems like an oxymoron, right? So your fluid statics means the fluids aren't going anywhere. So how can we look at them as if they're accelerating? Well, if you're in an airplane and the airplane's taking off and going down the runway, and you have you're not allowed to have your drink in your hand, I guess, certainly on U.S. planes as you go down the runway, but the fluid in your glass would be accelerating even though it's not circulating. And so when we talk about fluid statics and we talk about accelerating fluids, that's the system we're looking at. We're thinking about the fuel that happens to be in the fuel tank of the plane, for instance, as it accelerates down the runway. It's being accelerated. It's not being accelerated in the same sense as the Bernoulli equation where you have it flowing along a streamline, but it's in a static tank, and the tank is accelerating down the runway. And maybe as a function of that, you can imagine the pressures might change. And so if you're going down the runway and you have a free surface in a tank, you can imagine that, well, you know, if you take a glass and you push it across a table, it'll slop up on the back side of where you're pushing it from. And so we should be able to calculate the behavior of that system for a system where we're interested in acceleration. So that's the next, perhaps, point that we might want to make. So static fluids, we're interested also in accelerating fluids. So that's the task that we've set ourselves. So how do we go about doing this? So we could take a beaker, the idea of a beaker, and we could do an analysis on that beaker, but beakers are not such a convenient shape for us. So let's go and do something that is a bit more convenient, and that is to take a differential cube. You know, you're wondering why you did calculus for all of your high school careers in a couple of years already. Well, we're going to put some of it to use, at least in an elementary form, no pun intended. And so what we can do is we can take a differential cube, which is an element. We always use this right-handed coordinate system. Remember this equation, dp dz equals minus unit weight. The coordinate system we'll always use is, in mechanics, we use a right-handed coordinate system. So right-handed coordinate system means x, y, and z on the thumb through your middle finger, is it? First finger? I don't know what the names are. And it's always with, in this class anyway, elevation z is always positive going upwards. And so that's the standard way in which we'll look at this. So in terms of this diagram, this is the x direction, this is the y direction, this is the z direction. We can look at this particular system in terms of the different components. It has some weight of this cube. You can imagine that we have a pressure acting upwards on this face. You can imagine that the height of this particular cube is some length which we'll call a small increment of z in the vertical direction. And all we need to do is we can do a force balance on this. And so the pressure rather, acting on the top, is going to be equal to some pressure at the bottom plus a change in pressure. Because we've gone some distance, we don't really know what that change in pressure is. But what we could do is we could figure out what that pressure is just by adding an amount, and let's multiply that amount by 1. And so dz over dz is just 1. So we've taken the pressure at the top, we've added a small increment of pressure, which we don't know, and we've multiplied that by 1. dz over z, dz is just 1, right? And so what that allows us to do is if we know something about this change in pressure, we should be able to calculate what the rate of change of pressure in the system with space. We should be able to calculate what this pressure is. So that's our interest in this. So what else is this? Well, we could imagine this area of the top here it's actually equal to, I don't think we need this, we'll keep it as area, but obviously in the same way we've written this as dz here, this increment here is going to be a small length in the x direction, dx, and this is going to be a small increment in the y direction, dy. So this is just dx dy. We won't necessarily use that. And then we can invoke our old friend Isaac to be able to solve this system. So you'll recognize this, of course. It may be written slightly differently from how you're using it. It basically says that the sum of all forces on a thing, system, a beaker, a plane, a differential block like this, all have to sum to equal the mass times acceleration. So if the forces are out of balance, if the sum of the forces in any direction don't equal each other, then by definition it has to be accelerating. It has to be out of equilibrium, and it's using up its inertia. The reason I underline these is because, of course, in this case, this comprises portions which are a force in the x direction, a force in the y direction, and a force in the z direction. Bless you. And it's multiplied by a mass, multiplied by accelerations in each of these directions, which we said that we would like to be able to apply. So the plane's going down the runway, it's accelerating. You can calculate what that acceleration is. And so in this particular case, let's also apply to this an acceleration. Always in this coordinate system, we resolve things positively in the direction of the axes. So if the z direction is positively upwards, then a positive acceleration is flinging something into the air, the elevator that takes you up. A negative acceleration would be going down in the elevator. And so we need to be aware of that. So let's, this is the full form of what we'd like to do, but let's for now just look at one component, which is going to be the force in the z direction is equal to the mass of this thing multiplied by the acceleration in that direction. And so let's look at each one of those components. So let's look at the forces that are acting on this component first. What do we got? Acting upwards. We have a fluid pressure multiplied by an area, which is this one here. We have a pressure that's acting downwards, which is going to be negative. So it's minus an area multiplied by this component here. So this is P plus a rate of change of pressure with elevation multiplied by how much that elevation change is. We have that. We have an amount here, which is its weight. It's acting downwards, so it's negative. And so what is the weight going to be? It's going to be the unit weight of the fluid multiplied by its volume. And the volume has to be equal to the area multiplied by dz, right? By definition, right? This is the cross-sectional area here, and this is the height. And that has to be equal to this inertia. So the whole left-hand side of this is sum of the forces in the z direction, and it has to equal the mass times acceleration. So the mass is going to be the volume again multiplied by density, and of course this volume is also this same thing, and it's going to be multiplied through by this acceleration in the z direction. Sorry, A, not Z, A sub Z. So those are all the forces that are acting on this. And so that absolutely defines what's going on in the system, and so we can actually reduce this to be able to figure out what some of the components are. I guess if I write it out in longhand, well, actually I don't need to write it out in longhand. Let's get rid of some of these things. We have a pressure here and a pressure here that cancel out. They're both multiplied through by the same thing. We're left then with this term multiplied by an area, and so maybe we can write this out as an area times dp dz times dz minus an area times dz times a unit weight, and that's equal to an area times dz times density times acceleration. And so you see that we can cancel out all of the a's, we can cancel out all of the dz's, and we're left with an expression which is, if I remember this, change in pressure, I'll write it a partial because it's more useful for us to use it that way. Unit weight is equal to density times acceleration in the z direction. And actually in your notes, in the equation sheet, we'll just rearrange it so it's all on the other side of 0. So the other, this is just rearranging it. And just because it's a convenient way to remember it, minus density times acceleration in the z direction equals 0. So that's a fundamental relationship that we've defined. And that is come from resolving behavior in the z direction. And I guess physically what it says is that if we have an accelerating fluid, then there's some difference in the pressures that we'd have in the system, and you know this, right? You know that if you, we as humans are not, actually we're mainly fluids, right? We're mainly liquid of some description, some of us mainly water, a bit of fat as well, I guess. And so you know that when you go up an elevator, your knees feel it, and so you feel the force of your body being accelerated. And so I suppose you could think that that is related in some way to a change in pressure. You're feeling more pressure on your soles of your feet, so the fluids in your feet must also be feeling the increased fluid pressures because that has to actually hold you up. So there's some equilibrium in your body. And so in the cases where we're not looking at statics but looking at accelerating fluids, then we have to think about this term. But of course, when it's a static fluid and we don't worry about this term, we're left with exactly the same relationship we had before, which is change in pressure with elevation and unit weight, and the acceleration goes to 0. So that's a standard equation for us as we go in elevation. So what we can also do is we can also look at the behaviors in the other directions. So we've looked so far at going vertically. What happens as we go horizontally? We can do the same thing. We could, for instance, put a pressure on this side. We can put an acceleration going, well, actually, let's do the next one on the back side of this and the front side. This would be the pressure acting in the x direction. I'm not going to derive this. There would be a acceleration in the x direction, and we could look at the behavior. So if we did the same thing to resolve in the x direction, and I'm going to do it down at the bottom here because I guess I'll just do these in reverse order. I'm going to put y above it, but I'll do x first. So in the x direction we have everything exactly the same as before, except we don't have weight acting against us. Because now we're going horizontally, we go from one location to the other, weight acts perpendicular to that direction, so there's no influence. And so just by induction, if you like, the expression that will describe our behavior would be this. Change in pressure in the x direction, this term doesn't exist, minus the density of the fluid multiplied by its acceleration now in the x direction equals 0. Bless you. And we can do the same thing in the y direction again, horizontally. We're resolving forces horizontally, so weight is perpendicular to that direction, and so the changes in pressures we get in that direction are also going to be very similar, where we just switch all the subscripts that are applied to this, and those are exactly the relationships that you see in your book and that we'll try and use in this class. So these three relationships are fundamental to what we're dealing with. They say that if we're not accelerating a fluid, if the fluid truly is static and not accelerating, then in all cases these acceleration terms are 0 and we're left only with these components. And I suppose for static fluids that aren't accelerating, then the important relationships that come out, which really are truly fundamental to this course, are this one. Again, for our coordinate system, this is the negative sign, which just means that for us up is positive z. And from these expressions, both of these are identically that the pressure in the y direction is equal to 0, which is also equal to the change in pressure in the x direction. So this is if ax equals ay equals az equals 0. So if it's not accelerating, then these are the simplified expressions that we're dealing with. Okay? And so those are fundamental to what we'll deal with in this class. So the next step is, how do we actually use those in some useful way to be able to figure out exactly what's going on in our system? So the interpretation, if you like, in English for each of these is that as we go down in elevation, then the rate at which the pressure changes is controlled by the local magnitude of the unit weight. If the unit weight happens to be changing and reducing as we go up, then we'll get that curved pressure curve as we go up, and we can figure out exactly how we can get that from this expression. But the other important component of this is it says that the pressure changes as we go laterally don't change. And so this is saying that if you're sitting in a swimming pool and you happen to be at some elevation, so this is xy and this is z, and you happen to be swimming horizontally, and you end up at the same elevation beginning and end, then because the pressure doesn't change as you go horizontally, it changes vertically but not as you go horizontally. So if you go laterally from one point to another, then the pressure has to remain the same. And so that makes sense as well, that if you go just underneath this surface, you'd imagine that you go across this free surface. The definition of a free surface is that the pressure is the same. In absolute pressure, it'd be equal to atmospheric pressure. So P absolute would be 10 to the 5 pascals, roughly, right? Atmospheric pressure. And as you go down below this, then we could calculate how the pressure changes with depth as we go down there. So it changes with elevation, with the z direction, but not horizontally as we move across a system. So that's an important observation. And that's just the translation of each of these components. The other thing which hasn't come out of this analysis, which is also kind of a fundamental observation, is that the pressure, we haven't used this terminology, but the pressure in the x direction is equal to the pressure in the y direction, which is equal to the pressure in the z direction, acting on this cube. And so we just refer it to it as pressure. And so the three components come out. dP dz is equal to minus unit weight, always true. The changes in pressure as you go horizontally doesn't change. dP dx and dP dy is equal to 0, which is the interpretation of that. And the pressure at the point is always the same in all directions. Not true for solids, but certainly true for fluids that we're dealing with. And so then comes the question of how do we translate this into something useful to be able to say something about the systems that we were looking at before, and that is to maybe to calculate whether your watch, which is good apparently to 300 meters, will sustain the pressures as you go down in the fluid, or how the pressures on a body would change as you go down this. So this is actually amazing stuff. But anyway, so how do we do that for each of these two systems that we'll deal with? So the two systems that we're going to deal with are, I guess the easiest one first is an incompressible fluid, and we've kind of already done that. So for an incompressible fluid, so this is fluid pressures with depth. So the easy one is for an incompressible fluid. What's an incompressible fluid mean? It means, I guess, that density equals constant mainly with pressure, but I guess also with temperature as well, maybe, but mainly pressure. So we're talking about liquids. Liquids, it's, if you like, it's code for liquid. As we talked about in terms of compressibility, right? We talked that liquids are incompressible, don't change density very much, and don't change volume as you apply pressure. Gases in your bicycle pump do. And so how do we calculate how pressure would change as a function of depth? And we use depth, but typically we use this, well, not typically, we use this coordinate system which is positive upwards. So what do we have? We have change in pressure with elevation is equal to minus unit weight. And so we want to be able to calculate how pressure changes as a function of elevation. And so it's really quite straightforward. We have an elevation 1, we have an elevation 2, we have a pressure at elevation 1, and we have a pressure at elevation 2. This is a P, by the way. It looks a bit like a rho. So, simple calculus. Change in pressure is equal to minus unit weight multiplied by change in elevation. You integrate between two limits. You assume that unit weight is constant, so we can take it outside the integral. You integrate between pressures 1 and pressures 2, and elevations 1 and elevations 2. It's a very simple integral. Pressure evaluated between those limits, P1 and P2, is equal to minus unit weight times elevation at elevation Z1 and Z2. Substitute the limits and you have the change in pressure between them is equal to minus the unit weight times the change in elevation between them. So, calculus does have some uses, lots of uses. So in other words, if you want to calculate the pressure at point P2, it's just equal to the pressure at point 1 minus the unit weight times the change in elevations between these 2 points, or coordinates between these 2 points. And you realize that in our coordinate system, Z2 is a smaller number than Z1, right, by definition. And so this is always going to be negative. And so the other way to be able to define this, typically you might want to do this, is that if you classify this height here as h, you can just write this as P2 is equal to the pressure at point 1 plus the unit weight times h. So that's typically the way you'd have seen it. And you know that, I think, probably from your understanding of physics before this class. And so that's a standard relationship, and it's no different from the analog that we put together of being able to define behavior for these stacked paint cans full of air, weightless paint cans full of air that give us our pressure at a particular depth. So that's the easier of these cases, but it's definitely for an incompressible fluid, one that doesn't change with density. So what happens if we then look at the case where we have a compressible fluid? So do I want to, I guess I can squeeze it on there. You probably have that. You can go back to these. So now if we look at a compressible fluid. And so the definition of compressible fluid is the alternative to an incompressible one. We know, for instance, that the change in pressure with elevation is equal to minus unit weight. And we know that this is also equal to minus the density times gravity. We're assuming that gravity doesn't change, but we could presume that the density will change. We know from the ideal gas law that the pressure is equal to density times RT. Gas constant for that particular gas multiplied by its absolute temperature, absolute pressure, of course. And so we could define density as equal to pressure over RT. and presumably we can substitute that back in here. So we have the change in pressure with elevation is equal to gravity times pressure times RT minus. We know that we have pressure on both sides of this equation, so we can just rearrange that as the change in pressure divided by pressure is equal to minus gravity times divided by RT times elevation change. And so what we could do is we could rearrange that to be able to integrate it. We can integrate again, just I won't redraw the diagram, but this is the same diagram, elevations changing in pressures. And so the pressures we want to integrate between are a pressure at point 1 and a pressure at point 2. Gravity is the same. Let's say the temperature remains the same. It's isothermal. And so this is elevation 1 and elevation 2. And if we do that integral, we end up with log P evaluated at those 2 points is equal to minus G over RT. Get rid of that. And just this, the integral of this is Z2 minus Z1. I guess I'll write it out in this form. And so if you want to substitute these limits, then it ends up being just log of pressure differences at the 2 different locations, just by substituting these and realizing that a log minus a log is just the ratio of the 2 magnitudes, which is equal to gravity RT over, it's just going to be Z2 minus Z1, right? And so you can exponentiate that and do some fancy things, which we'll do in a future class. But you can see now it's not the same relationship as we had previously, which was this. And you can rearrange it by you can exponentiate both sides to be able to get these separate from each other. I guess actually we could do that, right? We could do P2 over P1 is equal to the exponential of the whole thing, right? G Z2 minus Z1 over RT minus. And so, not sure exactly what that would look like, but we can plot what we think it might look like just from our kind of understandings of the heuristics of this. And that is if we plot pressure changing as a function of location, what do we know? We can just rationalize the fact that if we look at elevation going upwards and pressure being on this horizontal axis, if we start off at some pressure, we know that as we go up to the next step, then the change in pressure with elevation is absolutely equal to this magnitude. And so we could do this little differential diagram of dP versus dz, and that would get us to this initial point here. But the point is, as we go up successively to each differential amount above us, then all we're doing is that the magnitude of this slope is changing. And so if this unit weight is reducing as we go up and reduce pressure, then what's going to happen is that this is physically going to get steeper and steeper and steeper. And so that incrementally, each of these individual increments of change in elevation and the change in pressure, every time you go up the same increment of height, the change in pressure will be less because you've got a less heavy, weightless can of stuff above you. And so we know now, if we want to be able to calculate, for instance, our magnitude of our pressure at the top of Everest, which is at 10,000 meters, relative to sea level, which is at 0 meters, then we have a way of being able to do that, because from the ideal gas law, it tells us something about how the density of this fluid changes as we go up in elevation. And so you can plug the numbers in and do the calculation, but immediately you can see just from looking at this figure, if we assume that the density is constant, then the trajectory we'd have to go up on would be this, right? So definitely the change in pressure from this sea level magnitude to the top of Everest will be less if we account for the fact that the gas is compressible, because as we go up, we're not following this constant trajectory. And so this constant trajectory basically said that by the time we get up to 10,000 meters, the pressure is zero. We know that's not the case. We'd explode. It'd be like being in outer space. You'd have to wear a spacesuit to go up to the top of Everest. Not just for breathing, but to stop your body from exploding from the inside out. And so all this does is actually account in a reasonable way to accommodate this. So this relationship, of course, is true for the cases where the gas is compressible, and it allows us to be able to calculate exactly what this would be. You can do the calculation yourself very simply. I won't do it here. But it allows us to, at least to be able to rationalize that misobservation that going up 10,000 meters, you'd be at zero pressure as you get up to the top of Everest. So what else? So I guess the only other thing I'd make the point of saying is that in this, each of these compartments, which we'll deviate from, we've gone through about 15 pages of derivations, which you don't have to go through to get to this point. And so next time we'll recap these things and go on through. So I think this is a much simpler explanation, I think, than is in the book. It's perfectly adequate for what our needs are. We have this differential statement that we've used to be able to calculate how pressure changes with height. And we're all ready for the next class, I think. Great. Thank you.